Hey everybody, today we're looking at section 2.3 notes. So we're officially going to define what a continuous function is. So continuity is talking about a continuous function. Typically everything's continuous. There's no problems. You have this curve going from left to right, everything we've been dealing with. There are a couple issues we've seen, and this will kind of break it down. But let's go back a step here. Let's talk about the main point about limits. So what section 2.1 really focused on is how do you determine if a limit exists at a point? And what we said, and we kept saying, was if the limit from the left is equal to the limit from the right, then the limit exists and it is equal to that value. So if the limit from the left is equal to the limit from the right, then the limit exists and it is equal to that value. And then here's kind of the shorthand way of saying that. So the limit from the left is equal to the limit from the right, then that limit exists at the point. So that's the main point about limits and how we determine if a limit exists. So then the next level is if the limit exists and that limit value is equal to the function value, then the function is continuous at that point. And here's the short way to write that. So if the limit value is equal to the function value, then that function is continuous at that point. So first, you need to determine if the limit exists. How do we do that? Well, if the limit from the left equals the limit from the right, then the limit exists and it is equal to that value. And then if that limit value is equal to the function value, that function is continuous at that point. And that's really what our main focus of today is. So let's talk about the problems. Like, where do we have problems? Because for the most part, everything's fine. There's no issues or anything. But what we've seen so far is the type of discontinuity. So we have a hole, we have a jump, we have an infinite. And we're really just going to deal with these three. Oscillating is nothing that's going to come up this year for us. It is a type of discontinuity, and it happens with functions like sine of 1 over x, where there's a really dramatic change at a certain point. So we're not going to deal with that. We're going to focus our attention on these first three. So we've seen holes, and what happens at a hole is the limit exists, it's just not equal to the function value. So either the function value doesn't exist, or like those other cases when the function value is just somewhere else. So whenever limit value does not equal function value, that's a hole. And we're also going to call that removable. That's a removable discontinuity. And these are going to be called non-removable. What a removable discontinuity means is it's the only type of removable we're going to deal with. Removable discontinuity being a hole, it's just a different word for a hole, is that like if you can plug the hole, like if you put one function value in that hole, you can actually plug it. I always picture like a dam, and there's like one little hole in the dam, you kind of put your finger in it and it's plugged the hole, so there's no issue. So the hole is a removable discontinuity. And how you can algebraically determine, so graphically I can just see, oh look, there's a hole there. How you can algebraically determine a hole is if the limit does exist, it's just not equal to the function value. So you're approaching something from the left and from the right, but what's there isn't that same value. So either nothing is there or it's some other function value. For a jump, I can see the jump here. So I see the limit from the left is equal to something and the limit from the right is equal to something else. So in the case of a jump, the limit does not exist because the limit from the left does not equal the limit from the right. And specifically for a jump, what you'll see is that the two one-sided limits will exist. They're just not equal to each other. And the function value may exist. It may not. It could be two open holes, but it can exist or not, the function value at that a. So in this case, f of a is equal to that value there. So the main idea of a jump, which is a non-removable, I mean, you can't just plug that hole. It's a big gap. A jump is a non-removable discontinuity. Is the one-sided limits exist, they're just not equal to each other. So the limit does not exist. And if the limit does not exist, you cannot be continuous. Because in order to be continuous, you need limit value to equal the function value. So if the limit doesn't exist, you cannot be continuous. And then an infinite discontinuity is, again, we can determine this right away, because if we plug in that a value into the function, you'll get a number over 0. Anytime you get a number over 0, that will be a vertical asymptote every single time. When you get 0 over 0, that's usually when we get our holes. But a number over 0, we have a vertical asymptote. And that definitely is a non-removable discontinuity. You definitely can't plug that hole because it's infinitely wide. So the limit at a vertical asymptote doesn't exist. You could say that the one-sided limits exist because they would be positive or negative infinity, depending on the side. So in this case, the limit as x approaches a from the left is positive infinity, and the limit as x approaches a from the right is negative infinity. And the function value definitely does not exist at a vertical asymptote. Again, it can exist at a jump, just one of the 2 points. Like I said, oscillating, I'm not going to talk about. So here's what I was talking about with like plugging that hole. So say I have some function like 2 sine of x over x. So let's check that out for a second on our calculator, because this is that sine of x over x coming up again. So I just wanted to look at this real quick here. Let me pull my calculator up. Like the limit as x approaches 0 of sine x over x equaled 1. That was the thing that I wanted you guys to memorize. So this one is, create my fraction, 2 sine of x over x. And make sure you're in mode radians. And let's set a window of like, I like my -5 to 5. So now we're seeing like, oh my gosh, this one looks like it goes through 2. So the limit as x approaches 0 of sine x over x was 1, if you remember that. And this one is looking like it's equal to 2. And if we go in, let's do our table set. Just to kind of check, let's start at 0. And let's count by 0.01s. And then, oh yeah, look at that. That's definitely approaching. Look at that. On either side of that 0, we're approaching that y value of 2. So we're kind of seeing that happening here. Algebraically, how can you determine that? Well, again, if you graph this, what's going to happen is all of this, and there's that little hole in there. So like, how do you plug the hole? Like, can you create a piecewise function that plugs the hole? Because there's one point that's missing. And how you would do that is you could say that y is equal to, or the function is equal to 2 sine of x over x everywhere except for 0. And then say, have the function equal to at x equals 0. And what this will do is it'll plug the hole. It's a way to plug in a removable discontinuity. And just doing this algebraically, like how can you determine where that hole is? Because I told you to memorize that the limit as x approaches 0 of sine x over x is equal to 1. So if I wanted to solve this problem of 2 sine x over x, I can use those limit rules. Remember, these are two things multiplied together. It's like a 2 times sine of x over x. So I can take the limit as x approaches 0 of the 2 function times limit as x approaches 0 of sine of x over x. And again, there's not an x down here as well, because that would be x times x, which is x squared. It's just 2 times this divided by this, and I left all of that on the right side. Now we're not adding the fractions, we're multiplying. So this does not have an extra x down here. And then this limit, again, this is the line y equals 2. So when x approaches any x value, the y values are going to approach 2 always. And then this, the limit as x approaches 0 of sine x over x, we memorize equal to 1. So this is equal to 2. And then that is the value that will plug in. Again, just going back to the beginning, again, if you determine the problem, if I plugged in 0 in to 2 sine x over x, sine of 0, that's the y length of the reference triangle. So if I hold my hand at an angle of 0, that y length is 0. So sine of 0 is 0. 2 times 0 is 0 divided by 0. 0 over 0, indeterminate form. More work to do. Our more work in this case is to memorize that limit as x approaches 0 of sine x over x is equal to 1. And that's equal to 2. That's our more work in that case. Okay, so here's like our classic calculus problems that we're going to be doing in this section. So we're dealing more with these piecewise functions. So thank goodness we dealt with all of that hard work in that chapter 1 of these piecewise functions. So my question here is this function continuous? So algebraically, what we can do is First, we need to determine, if we need to determine continuous, first we need to determine, does the limit exist? Because if the limit does not exist, then it's game over. Then determine the function value. And if function value equals limit value, you are continuous at that point. Because the only issue here is going to be at the connection. This is a line. Lines are continuous. This is another line. Lines are continuous. The only issue for this piecewise is the connection point. So if I check the limit from the left, that's putting 2 into this piece here. If I put 2 into this piece here, I get 3 minus 2, which is 1. And again, even though 2 doesn't belong to this function, 1.999999 does. So by plugging 2 in, what we're checking is, where is this function going as you approach 2 from the left side? That's equal to 1. If I check the limit as x approaches 2 from the right, I want to put 2 into this function here, and I get 2 over 2, which is 1 plus 1 is 2. So the limit as x approaches 2 from the left was 3 minus 2, which is 1. The limit as x approaches 2 from the right is 2 over 2, which is 1 plus 1 is 2. Since the limit from the left does not equal the limit from the right, the limit does not exist. Since the limit does not exist, you cannot be continuous. That's our flow of knowledge on that problem. You can check if you want f of 2. Let's see where 2 belongs to this piece here. So I'm going to put 2 into here. F of 2 is equal to 2. But since the limit doesn't exist, there's no way you can be continuous. So first check limit existing, and then check if limit value equals function value. And if it does, you have a continuous function at that point. That's the idea. And then maybe I'll just kind of go real quick how to do it piecewise on the function again. So you can kind of check that out as a nice friendly reminder. So let's see. Let's do, in parentheses, 3 minus x. And then we're going to do x. So we just did that all without a calculator. But if you want to actually see it, oops, 1, 2, x less than 2. So again, that was the second math button, which is test. That's where you get those symbols there. Okay, so there's that piece. And then I'm going to put in this x over 2 plus 1 x second test. I'm going to hit number 4, greater than or equal to 2. And then if I graph that, I am seeing a jump discontinuity. So, and that's what this was showing me here algebraically. The two one-sided limits exist, they're just not equal to each other. So that's how you can determine algebraically if you have a jump discontinuity. If the two one-sided limits exist, they're just not equal to each other. And graphically, I'm seeing that right here. There's that jump right there. Again, how to put that in again. Put the first function in a parenthesis, and then on its interval, scoot over just to the right here so you can see that, x less than 2. Don't forget second math, that test button is where you get those symbols. And then add the second piece, x over 2 plus 1, parentheses, open it up, x greater or equal to 2. Okay. Okay, so this is kind of another interesting one. This is a classic calculus problem. It wants you to make this thing continuous. So I have some line. If a is 1, this is the 2x line. If a is 2, this is the 4x line. If a is 3, this is the 6x line. But I don't know, it's 2 times some a number x. And the other function is x squared minus 1. And it connects at 3. So again, lines are continuous everywhere. Parabolas are continuous everywhere. So I need to figure out the value that I'll put here to make those two things connect. Okay, so what I'm going to do here is first I'm going to check the limit as x approaches 3 from the left. Because what I need is the limit as x approaches 3 from the left to equal the limit as x approaches 3 from the right. Because if the limit from the left equals the limit from the right, then that limit exists and it's equal to that value. And then if limit value equals function value, you're continuous at that point. So if I plug 3 into this equation here, I get 9 minus 1 is 8. So plugging 3 in is checking the limit from the left by plugging 3 into x squared minus 1. I'm going to plug 3 into this thing here. and I get 2 times a times 3. That's the limit from the right by plugging 3 into the right piece. And what I need these two things to be the same. I need the limit from the left to equal the limit from the right. Well, this is 8 equals 6a, so then a is equal to 4/3. So this line here has to be the 8/3 x line. In order to make this continuous, that line needs to be the 8/3 x line. And then if you check, so the limit value, if I plug in 8/3 is equal to the limit from the left, will equal 8/3. So that's 64/9. This will be, so from the left, 64/9. That's 8/3 squared minus 1 minus 9/9 is equal to 55/9. This is the limit as x approaches. Oh, that's not true. I am sorry. I'm putting in the wrong number. Let me erase all that. No, because the a is 4. This was the a number to determine the function. I want to plug 3 into the left. If I plug 3 into the left function, I get 8. If I plug 3 into 8/3 x, I get 8 times 3 divided by 3 is 8. So since the limit from the left is equal to the limit from the right, which is both equal to 8, the limit exists and it is equal to that value of 8. So the 4/3 is the a value I plug into there to create the 8/3 x line that'll make this continuous. And then if I plug 3 into the function, f of 3, plugging 3 in, f of 3 is equal to 8/3 times 3 is equal to 8. So the limit value is equal to the function value is equal to 8. So I found the a value that is going to make this a continuous function. The line x squared minus 1 and 8/3 x connects up at x equals 3. That's like a classic calculus problem. So here's our first of 3 existence theorems. So what the intermediate value theorem does, it's what I like to call is like the elevator problem. What it breaks down to is like, say you enter the elevator at Jones on the 1st floor and the doors close and then they open on the 5th floor. What it guarantees you is at some time when you were on that elevator, you were at the exact 3rd floor height. You were also at some time equal to the exact 2nd floor height and 4th floor height, or any other height between the 1st and the 5th floor. So if you can imagine, because time is continuous, you didn't teleport up, at some time you hit every floor on the way up from the 1st to the 5th floors. Now I'm not telling you what that time is, I'm just proving that a time does exist. So that's what the intermediate value theorem guarantees you. You're guaranteed to hit every y value on a function between the endpoint y values. But in order to use it, you need a continuous function on a closed interval, meaning you can't have any jumps, any of these discontinuities. No, you can't have any discontinuities, and you need the endpoints. Closed interval means brackets, meaning you have both endpoints. And if you do have those two things, you're guaranteed to hit every y value at some point at some x value that I don't know what that x point is. Let's see it in action. So let's say I have this function, x cubed minus 5. And what if I asked you to guarantee me an x-intercept, f of x equals 0, on the interval 0 to 2? Like, how would you do that? Well, again, if you notice, I'm not even asking for the specific x value. This one we can actually solve for. If you wanted to set it equal to 0, add 5 cube root, if you wanted to solve for it. But just to kind of show you how this works, is if you plug 0, this is a continuous function. This is a cubic function, and it is continuous. If you plug 0 into this function, you get 0 minus 5 is negative 5. If you plug 2 into this equation, you get 8 minus 5, which is 3. So at an x value, this is the closed interval, bracket 0 to 2. On this closed interval, we went from a y value of negative 5 to a y value of 3 for a continuous function. So you're guaranteed to hit every y value at least once. It could be more times, but at least once between negative 5 and 3 on that x value between 0 and 2. So here's how you would write your answer. And this is the fancy calc way to write it. Since f of 0 equals negative 5 and f of 2 equals 3, and since f of x is continuous, then this is a fancy way to say there exists, a capital backwards E. There exists some C, and C stands kind of like for an x value. It's a specific x value. There exists a C such that, ST such that f of C is equal to 0 on, as long as that C value is between 0 to 2. So that x value between 0 to 2 by IVT. That's how you would say it. So since f of 0 equals -5 and f of 2 equals 3, and since f of x is continuous, then there exists a C such that f of c equals 0 on the open interval 0 to 2 by the intermediate value theorem. So the first of 3 existence theorems where we prove the existence of a solution, but we don't actually say what the solution is. So hopefully you had fun with this today. We'll see you guys in class. Take care.